Hydrological and hydraulic design of bridges. In previous video lectures, we studied how do we calculate the maximum discharge for which a bridge is designed. There are many ways to calculate. The first one being by making use of some empirical formulas which we studied, like that of Dickens formula, the Rives formula, the Ali Nawaz Jang Bahadur's formula, and the Inglis formula. The next method is that by using the rational method, which involves the rainfall and other characteristics of the area where we are proposing to construct a bridge. This is the second one. The third one we studied is by the area velocity method, in which we take the hydraulic characteristics of the stream into consideration, like that of the cross-sectional area and the slope. The fourth one being the unit hydrograph method, and the fifth one being from any available records of the flood discharges which are observed at that particular bridge site, or from any other available site in the vicinity of that proposed site of construction of a bridge. All right, so we studied empirical formula in detail. Today's topic is the rational method. How do we make use of rational method to calculate the maximum discharge for which a particular bridge is going to be designed? All right, now before starting the rational method, we need to know a lot of things, so we'll study one by one each and every one of that. So rational method is a method in which we take the rainfall characteristics of the area into consideration, all right, to calculate the maximum discharge or the peak discharge for which a bridge will be designed at that particular site in that catchment area, and taking rainfall characteristics into consideration, like that of intensity, duration, etc. All right, so rainfall on an area is expressed as so many centimeters over the entire area for a certain fixed interval of time. All right, rainfall on an area is expressed as so many centimeters over the entire area for a certain fixed interval of time. But all the water which is coming down from the rainfall is not available for further use. Why? Because some quantity of it is lost in evaporation, some of it may be lost in percolation, and some of it may be lost in transpiration. All right, so all the water that is coming down from the rainfall is not available for further use. Why? Because some quantity of it is lost in evaporation or percolation or transpiration. Evaporation is the loss of water from the land and water surfaces back to the atmosphere due to action of heat of sun. All right, whereas this percolation, this indicates the loss of water which is penetrated into the soil. Students, you must know the difference between interception and percolation. Very important to know here. While as this interception, this means the immediate seepage of water into the soil below, but the deep down travel of it to enter the groundwater, traveling through all the porous material, rods, etc., to reach the groundwater, that process is known as percolation. Whereas the immediate entry of water into the soil below is known as interception. All right, so all the water which is coming down from the rainfall is not available for further use. Why? Because some of it is lost in evaporation, some in percolation, and some in transpiration. Whereas evaporation is the loss of water from land and water surfaces back to the atmosphere due to action of heat of sun. And whereas this percolation, this indicates the loss of water penetrated into the soil, and transpiration is the loss of water caused by the leaves of the growing vegetation. Leaves of growing vegetation. We are studying the rational method for calculation of maximum discharge or the peak discharge for the design of hydraulic structure, that's a bridge. But before learning about the rational method, we need to learn about some of the important topics. So we are taking them one by one. All right. So transpiration is the loss of water which is caused by the leaves of the growing vegetation. Now the net quantity of water which remains on the surface after all the losses, that is termed as surface runoff. All right. What is surface runoff? Surface runoff is the quantity of water which remains on surface after all the losses. That quantity of water is known as surface runoff. Alright. And we also know that when the intensity of the rainfall exceeds the abstractive capability of the catchment, surface runoff occurs. Alright. Let me rub it first. So when the intensity of rainfall exceeds, when the intensity of rainfall exceeds what? The abstractive capability of the catchment, surface runoff occurs. Alright, so surface runoff will occur when the intensity of the rainfall exceeds the abstractive capability of the catchment. And we already came to know that this surface runoff, this is the water, the quantity of water which remains on surface after all the losses, that is known as surface runoff, right? Because all the rainfall which is coming down on the catchment is not available for further use. Some of it is lost in evaporation, some in percolation and interception, and some in transpiration. All that quantity that remains available is known as surface runoff. And we also know that when intensity of rainfall this exceeds the abstractive capability of the catchment, the surface runoff will occur. And eventually when large amounts of surface runoff concentrate, they provide large flow rates which are known as floods. All right. And the study of floods, their occurrences, their causes, their transport and effects is the very essence of flood hydrology. All right. So when the large amounts of surface runoff concentrate, they provide large flow rates which are known as floods, and the study of floods, their occurrences, their causes, transports and effects is the very basic essence of the flood hydrology. Now this rainfall in general, this varies in space and time. All right. However, under certain given conditions, it may be fairly assumed that it be either, let me write it down for you, that it may be either, number one, constant in both space and time. Second, constant in space but varying in time. And the third one, varying in both space and time. All right. So generally this rainfall varies in space and time both, but however under certain given conditions it is possible to assume the rainfall to be either constant in both space and time, constant in space but varying in time, or varying in both space and time. Now which thing will help us to judge that how we'll assume a certain given condition for a given catchment? The catchment scale. The catchment scale helps us to determine that which one of these assumptions is justified on practical grounds. All right. And what does this catchment scale mean? And how do we characterize these catchments based on this catchment scale? In terms of their area, in terms of area of the catchment. All right. So the catchment scale helps us to determine that which one of these assumptions, 1, 2, 3, is justified on practical grounds. All right. And generally small catchments are those in which runoff can be modeled by assuming constant rainfall in both space and time. All right, students. Small catchments are those in which runoff can be modeled by assuming constant rainfall in both space and time. Mid-sized catchments are those in which runoff can be modeled by assuming rainfall to be constant in space but varying in time. All right. And large catchments are those in which runoff can be modeled by assuming rainfall to vary in both space and time. All right. So it's the catchment scale which helps us determine that which one of these assumptions is justified on practical grounds, because we already know that rainfall varies in both space and time. But however, under certain given conditions, we can possibly assume the rainfall to be either constant in both space and time, constant in space but varying in time, and varying in both space and time. But catchment scale gives us fair idea about how we can make any one of these assumptions justified on practical grounds, and we term small catchments as those catchments in which runoff can be modeled by assuming constant rainfall in both space and time. Let me write it down for you. Small catchments, mid-sized catchments, and large catchments. Small catchments, mid-sized catchments, and the large catchments. Small catchments are those catchments in which runoff can be modeled by assuming constant rainfall in both space and time. All right. Now, mid-sized catchments are those in which runoff can be modeled by assuming rainfall to be constant in space. Rainfall is constant in space, but it varies in time. And large catchments are those catchments in which runoff can be modeled by assuming rainfall to vary in both space and time. All right. So this was about rainfall, the abstractive capability of the catchments, the surface runoff, and the catchment scale. The next thing is time of concentration. Before we are formally studying rational method, we are learning about certain terms, because this rational method is based on the rainfall and other characteristics of the area which are to be taken due care of. All right, students. Time of concentration. What is time of concentration for a particular catchment? All right. Time of concentration for a particular catchment. This may be defined as the time taken by runoff to reach the site of the bridge or culvert from the farthest point on the periphery of the catchment. All right, students. Time of concentration, it is defined as the time taken by runoff to reach the site of the bridge or culvert from the farthest point on the periphery of the catchment. All right, let me show you a diagram and you may be able to see it here. All right, so this is the catchment. This is the periphery of the catchment. This is the stream. This is the bridge site. All right. What is time of concentration? Time of concentration is defined as the time taken Time taken by runoff to reach the bridge site or culvert from the farthest point on the periphery of the catchment. So the time taken by runoff to reach the bridge site or culvert from the farthest point on the periphery of the catchment is known as time of concentration, or we can alternatively also say that the time required for a parcel of water to travel from the farthest point of the divide to the catchment outlet, that is known as the concentration time. All right, so this is the periphery of the catchment, this is the bridge site, proposed bridge site, this is the farthest point, and this farthest point is known as the critical point. So the time taken by runoff to reach the site of the bridge or culvert from the farthest point, which is also known as the critical point, to the proposed bridge site is known as the time of concentration. All right, so this is the stream, this is the bridge. I hope it's visible to you. This is the stream, this is the bridge side, this is the farthest point on the periphery of the catchment, this is known as the critical point, and the time required for water or runoff to travel, or a parcel of water to travel from the farthest point on the periphery of the catchment to the bridge side, that is known as the concentration time, or the time of concentration. All right, so this farthest point on the periphery of the catchment is known as the critical point. Now this time of concentration, it depends upon certain catchment characteristics. Let me write it down for you. Let me drop it first. So the time of concentration depends on length of the catchment area. Time of concentration depends on length of the catchment area. It also depends on slope, roughness, and depth of flow. Slope, roughness, and depth of flow. And we can determine this time of concentration by a simple empirical formula, which is Tc, that is time of concentration, is equal to 0.89 into L cube divided by H whole raised to the power 0.385. Alright, so this is a simple relationship by which we can determine the time of concentration of a certain catchment, which is equal to 0.89 into L cube divided by H whole raised to the power 0.385, where Tc is the time of concentration in hours. Concentration time in hours. This thing L is the distance from the critical point to the site of bridge or culvert in kilometers. L is the distance from the critical point to the proposed site of construction of the bridge or culvert, and that too in kilometers. So L is the distance from critical point L is the distance from critical point to the bridge site or culvert site in kilometers. Please be quite mindful of the units while we solve the numericals. Alright, so these formula are devised for these units particularly. Now this thing, H. What is H? H is the fall in level from the critical point to the bridge site in meters. Fall in level from the critical point to the bridge site in meters. All right, let me show you this in diagram. This is the critical point, this is the bridge side or the culvert side. This has some level, reduced level, let us suppose RL1. This has some level RL2. So the fallen level from the critical point to the bridge side in meters, that is H in our formula for finding the time of concentration of that particular catchment area. All right, so we have some more formulas to determine the time of concentration. We'll be studying them also one by one. Let me drop it down for you first. So time of concentration may be defined as the time taken by a runoff to reach the site of the bridge or culvert from the farthest point on the periphery of the catchment. All right. Or alternatively, I can also say that the time of concentration is the time that is required for a parcel of water to travel from the farthest point or the critical point of the divide to the catchment outlet. All right, we'll be studying some more formulae to determine time of concentration of certain catchments and watersheds. All right, so next formula by which we can find the time of concentration of a particular catchment is known as the Richards formula. So this is the Richards formula to find the time of concentration. Tc is phi L cubed by h whole raised to the power 1 by 3. This is the Richards formula for finding the time of concentration of a particular catchment area, where we know that this is time of concentration, is the time of concentration in hours. This is L, this is H, we already studied. But what is this term? Phi. Phi is given by 9 by 4, 5280 divided by C square Ki. Alright, where K, this is coefficient of runoff. K is the coefficient of runoff. Now we have C, this is Basin's coefficient. Then we have I, this is intensity of rainfall. I is the intensity of rainfall, and all other things like that of L, H and Tc, they have the same meaning as we already discussed previously. Alright, so this is the Richards formula for calculation of the time of concentration. Another formula is Danson's formula. Another formula is Danson's formula. Danson's formula to calculate time of concentration is given by theta L cube H whole raised power 1 by 2, whereas this theta is 5280 divided by C under root of S and I. S is the slope, this thing is the slope of the catchment. S is slope of the catchment. Alright, and I is the intensity of rainfall. And all other things like that of L, H and Tc, they have got the same meaning as discussed in the previous equation. Alright, so this theta and phi, theta from the Danson's formula and phi from the Richards formula, they depend on the intensity of the rainfall and the nature of the soil in the catchment area, because we have a table wherein we can relate intensity of rainfall with the type of soil. We'll study that when we'll do numericals on this topic. All right, so this was about Denson's formula. And it must be noted that most of these concentration time formula, these are empirical in nature, and therefore they have somewhat limited application. All right. A well-known formula which relates concentration time to slope and length parameters of a catchment is known as the Kirpich formula, or howsoever you may like to pronounce this word, Kirpich formula. This is a well-known formula which relates the parameters of the catchment, like that of length and slope, to time of concentration. All right, and by this formula this is rather applicable to small agricultural watersheds. Let me write it down. Small agricultural watersheds with drainage area of less than 80 hectares. This Kirpich formula, this is applicable to small agricultural watersheds with a drainage area of less than 80 hectares. And this formula is Kirpich formula for finding the time of concentration is TC or capital TC. Please don't confuse yourself, it's one and the same thing. 0.06628 r raised by 0.77 divided by s raised by 0.385. Alright, so this is the Kirpich formula for finding the time of concentration of small agricultural watersheds with a drainage area of less than 80 hectares. Alright, and this is a well-known formula which relates the concentration time to slope and length parameters of that particular catchment. And by this we can find the time of concentration of these small agricultural watersheds who have drainage area of less than 80 hectares. And the formula is 0.06628 r raised by 0.77 divided by s raised to the power 0.385, where Tc is the time of concentration in hours, L is the length of the principal water course from the outlet to divide in kilometers, and S is the slope between the maximum and minimum elevations in meter per meter. All right, let me write it down and rub it first, or let me write it down over here. All right, Tc in the Kirpich formula is time of concentration in hours. All right, and L is the length of the principal water course from the outlet to divide in kilometers, and S, this is the slope between maximum and minimum elevations in meter per meter. All right, in meter per meter. So this is about the Kirpich formula. Another formula which is used for the estimation of the concentration time is that of Hathaway. Now let's study about Hathaway formula for finding the time of concentration. This was about the Kirpich formula. We already studied about the Richards formula and the Danson's formula and the empirical formula. Generalized empirical formula first. Alright, so another formula which is used for estimation of concentration time is that of a Hathaway, which is known as a Hathaway formula. And the Hathaway formula is Tc is 0.606 ln 0.467 raised to the power 0.467 divided by s raised by 0.234. All right, So the Hathaway formula is TC 0.606 ln 4 raised to power 0.467 divided by S raised to the power 0.234, alright? In which this N is the roughness factor of the catchment surface. N. This is the roughness factor of the catchment surface. And all other terms are same as in the Kirpich formula, L and S. Alright, so this is the Hathaway formula, which is used for estimation of concentration time. Alright, and this is the formula TC is equal to 0.606 ln whole raised to power 0.467 divided by S raised to power 0.234. Well, S and N are the same as that mentioned in the Kirpich formula, and this thing N is the roughness factor of the catchment surface. Alright, so we have a table wherein type of surface is related to the roughness factor used for the Hathaway equations. We'll discuss them while we do the numericals on the topic. Alright, so this was about the time of concentration and the various formula by which we can evaluate it. The first generalized empirical formula, then the Richards formula, Danson's formula, Kirpich formula, and the Hathaway formula. Alright. Rational method for calculation of the maximum or the peak discharge for designing the bridge. We are studying certain terms related to this thing because this method takes rainfall parameters and other characteristics like that of area of the catchment into consideration. Alright, moving on, let us study about catchment area and how do we calculate it to make use of rational method. Catchment area. Alright, so students, as we already discussed in the previous video lectures, that the catchment area is defined as the upstream area from the bridge site which contributes to the water of the river. Alright, so the upstream area from the bridge site which contributes to the water of the river is known as its catchment area. Now, how do we determine this catchment area? Because we have to make use of rational method, and in formulas we have to evaluate catchment area first, then only we can make use of rational method. So the ridge line is marked. Ridge line is marked on the topo sheet. Topo sheet are the maps, topographical maps. So the ridge line is marked on the topo sheet, and with the help of a planimeter, the catchment area of the river on the upstream side, very important, we have to take upstream and not the downstream side into consideration. Upstream side of the proposed bridge site is worked out. Proposed bridge site is worked out. Alright, so the ridge line is marked on the topo sheet, and with the help of a planimeter, the catchment area of the river on the upstream side of the proposed bridge site is worked out. If the catchment area is quite large, then what we do, if the catchment area is large, it should be divided into small sections with reference to rainfall and topography. Alright, if the catchment area is too large, we divide it into small sections based on or with reference to the rainfall and the topography. Then we calculate the discharge or runoff from each section, and then we calculate runoff from each section separately. Then we go on adding them together so that we can get the total discharge. Alright, so this was something about catchment area. We already know that the upstream area from the bridge site which contributes to the water of the river, that is known as its catchment area. And how do we determine it? A ridge line is marked on the topo sheets, and with the help of the planimeter, the area of the river on the upstream side of the proposed bridge site is worked out. Alright, and if the catchment area is quite large, Then what we do, we, based on the reference or with regard to the rainfall and topography, we go on dividing the area in small sections, and then we calculate the runoff from each of the section. We calculate it separately, then we go on adding them to find the total discharge. All right, so this was about the catchment area. Now, maximum intensity of rainfall. This is the rational method to determine the peak discharge or the maximum discharge. For designing the bridge, it takes the rainfall and other characteristics of the area into consideration. We are discussing them in detail one by one. Maximum intensity of rainfall. How do we arrive at maximum intensity of rainfall of a particular area? All right. The rainfall is measured by the standard instruments which are known as rain gauges. All right. Rainfall is measured by standard instruments which are known as rain gauges, and they may be automatic or non-automatic, but the Simon's non-automatic rain gauge is commonly used in India. You must be knowing this. Simon's non-automatic rain gauge is the one that we commonly use in our country. Is commonly used in India. And we place these rain gauges at certain points which are known as rain gauge stations to measure the rainfall. Rain gauge stations. And these rain gauge stations, they should be evenly distributed over the area so as to obtain the representative figure of rainfall for the entire area. They should be such placed so that they evenly tell us about the rainfall system or the situation of that particular area. All right, the rain gauge stations should be evenly distributed for a particular area so that we will obtain a representative figure of the rainfall characteristics of that particular area, and that should be, that should be a representative of entire area of that particular catchment which we take. All right. So for hilly areas, they are situated quite narrow, but for plain country, one station is provided for an area of about 130 square kilometers. All right. These rain gauge stations for hilly areas, they are situated nearer, but for the plain country, one station is provided for an area of about 130 square kilometers. And it's very important to consider this thing, that these stations should not be obstructed by roofs of buildings. Otherwise, we'll not get the true readings. They should not be obstructed by the roofs of the buildings, nor by the large trees or any other obstructions. All right. So by installing these rain gauges at particular rain gauge stations, the readings for record of daily rainfall are taken at an interval of 24 hours. And the monthly rainfall and yearly rainfall can then be worked out from the data of daily rainfall. Let me drop it first. Let me write it down for you. All right. So the Simon's non-automatic rain gauge is the one that we use commonly in our country, and we must place these rain gauges at stations in such a way, or we must distribute them evenly so that they give us a representative figure of that particular area. All right. And for hilly areas, the distance of the rain gauge stations is nearer, while as for that of the plain country, they are situated quite apart, and it can go as high as 130 square kilometers. And these rain gauge stations should not be obstructed by roofs of buildings or large trees or any other obstruction whatsoever. From the readings of daily rainfall, which is taken at an interval of 24 hours, we go on assessing the situation of monthly rainfall, and yearly rainfall. monthly rainfall and yearly rainfall. This data can be worked out from the data of daily rainfall, all right? And from the records of rainfall, the maximum intensity of rainfall of a catchment area of the proposed bridge site is obtained, all right? So from these records of rainfall, the daily, the monthly, the yearly, the maximum intensity of rainfall, of catchment area of the proposed bridge site is worked out. Of the proposed bridge site is worked. All right. So that is how we assess the maximum intensity of the rainfall of a particular catchment. All right. Next thing that we need to know before formally proceeding to know about the rational method is the runoff coefficient. Runoff coefficient. What is runoff coefficient? This term runoff coefficient is used to indicate the ratio of surface runoff from an area to total rainfall on that area. Total rainfall on that area in a fixed interval of time. That is very important. In a fixed interval of time, that is known as the runoff coefficient. All right, in a fixed interval of time, that is known as the runoff coefficient. So this term, the runoff coefficient, this is used to indicate the ratio between surface runoff from an area to the total rainfall on that area, and that too in a fixed interval of time. That is known as the runoff coefficient. And the value of runoff coefficient, it varies from 0.20 to 0.70. The value of runoff coefficient, it varies from 0.20 to 0.70, and it should be carefully decided because it depends on the combination of so many factors. So we can say that its prediction is, it becomes far from the exact science, all right? So it has to be quite carefully selected. Which parameter? The runoff coefficient. This needs to be carefully selected for a particular catchment, and this is the ratio between surface runoff from an area to the total rainfall on that area. The ratio between surface runoff from a particular area to the total rainfall in that area, and that too in a fixed interval of time, that is known as the runoff coefficient, and it varies from 0.20 to 0.70, and it should be selected carefully. Now we'll study about some of the factors which contribute to the flood flow or which affect this runoff coefficient. Let me rub it first. The factors which contribute to the flood flow or which affect a runoff coefficient. The first one is area of catchment. Area of catchment. The smaller the area of catchment, the smaller will the coefficient of runoff, and vice versa. Smaller the area of catchment, the smaller will be the runoff coefficient, and vice versa. So we can say that runoff coefficient, our runoff coefficient is directly proportional to the area of catchment. If it's small, it will be small. If it's large, it will be large. All right. The smaller the catchment area, the smaller will be the coefficient of runoff. The larger the catchment area, the larger will be the coefficient of runoff. So they have a direct proportionality. Second one, characteristics of catchment. Characteristics of the catchment. As already discussed, it's quite essential to study in detail the characteristics of catchment area, as they considerably affect what? The value of runoff coefficient. And the matters which we need to study in particular is that of size, slope, vegetation, porosity, climate, etc. So it's quite essential that we go on studying certain characteristics of the catchment, as they considerably affect our value of runoff coefficient, and the matters that need to be studied in detail vis-a-vis the characteristics of the catchment. They are of size, slope, vegetation, porosity, and climate. All right. The next factor which affects our runoff coefficient is the condition of ground at the time of rainfall. Let me rub it first and then we'll go on studying it. Runoff coefficient is a ratio between surface runoff to the total rainfall in that particular area, and that in a fixed interval of time. It varies generally from 0.20 to 0.70, right? Alright, and its selection should be done carefully. The third factor is condition of ground. Condition of ground at the time of rainfall. The condition of ground at the time of rainfall. If the ground is dry at the time of rainfall, it will absorb more water and the coefficient of runoff will be small. Alright, and for the ground which is wet at the time of rainfall, reverse will be the case. That means the runoff will be more. Alright, so the condition of ground at the time of rainfall affects our coefficient of rainfall. If the ground is dry at the time of rainfall, it will absorb more water and our coefficient of runoff will be small. If it's wet at the time of rainfall, already wet, then ground will not absorb much of the water and our coefficient of runoff will be large. Fourth factor, intensity of rainfall. Intensity of rainfall also affects our coefficient. Intensity of rainfall. If it rains heavily in short duration of time, the soil does not get opportunity to absorb all the water. That means it will increase the surface flow and consequently this coefficient of runoff will be increased or it will be large. So the intensity of rainfall also affects our coefficient of runoff. If it rains heavily and that too in the short duration of time, the soil will not get any opportunity to absorb the water. So the surface flow or the surface runoff will increase. Surface runoff will increase and so will our coefficient of runoff. Alright. The next factor which affects our coefficient is the interval between successive showers. Fifth factor, interval between successive showers. So the smaller the interval between successive rainfall showers, the greater will be the coefficient of rainfall. It's quite understood. If the interval is small between successive showers, that means the frequency of rainfall is large, our coefficient of runoff will be greater. If interval is small, runoff is greater. Alright. So the smaller the interval between successive rainfall showers, the greater will be the coefficient of runoff and vice versa. Alright. The sixth factor is season of rainfall. It also affects our runoff coefficient. Season of rainfall. The rainfall during hot season gives less flow than during the cold season. All right. So the season of rainfall also affects our coefficient of runoff. The rainfall during hot season gives less surface flow, that means less runoff coefficient, and the rainfall during cold season gives comparatively more runoff, that means more coefficient of runoff, the higher, the larger value. All right. Seventh one is yearly rainfall. This also affects our coefficient. Yearly rainfall. The greater the annual rainfall, the greater is the runoff coefficient, and vice versa. The greater the annual rainfall, the greater will be the runoff coefficient, and vice versa. All right. So the greater the annual rainfall, the greater the runoff coefficient, and vice versa. All right. So this was about the factors which affect our runoff coefficient. All right. So the runoff coefficient, it is dependent on, or its value is dependent on certain factors like that of the area of catchment, the characteristics of the catchment, the condition of ground at the time of rainfall, the intensity of rainfall, the interval between successive showers, the season of rainfall, and the yearly rainfall. All right. So this was about the runoff coefficient. All right. Then we'll study about the response of catchments, catchment response. All right. We have certain types of catchment response with regard to the rainfall occurring in that catchment. Let us study about them now. Types of catchment response. Types of catchment response to the rainfall happening in that particular catchment. All right. We have three types of catchment responses. One is concentrated catchment. Second one is super concentrated catchment. And the third one is sub-concentrated catchment. All right, so we have three types of responses of a catchment with regard to the rainfall happening or occurring in that particular catchment area. The first one being the concentrated catchment, the second one being the super concentrated catchment, and third one is the sub-concentrated catchment. All right, we'll study one by one about them. The first one is the concentrated catchment. I'll show you diagrammatically. This is a particular diagram for a concentrated catchment. All right, and this is a hydrograph, discharge and time. All right, so in this type of catchment response, the concentrated catchment response, the runoff concentrates at the outlet and reaches its maximum rate after an elapsed time which is equal to the concentration time. All right, so we can say that in concentrated catchment, the time of concentration is equal to the rainfall duration. All right, TR is equal to TC. In concentrated catchment, the time of concentration is equal to the rainfall duration in that particular area, because that's why the runoff concentrates at the outlet and it reaches its maximum rate after an elapsed time, which is known as the concentration time. Rainfall stops at this time. Rainfall stops exactly at this time, because in this type of catchment response, rainfall duration is equal to the catchment response, the time of concentration, sorry. So the rainfall stops at this time, and the subsequent flows at the outlet are no longer concentrated because not all the catchment is contributing. Therefore, the flow gradually recedes to zero and the recession limb is asymptotic. All right. The effective rainfall is also shown in the figure. All right. So this is the concentrated catchment response. In this type of catchment response, the runoff concentrates at the outlet and reaches its maximum rate after an elapsed time, which is equal to concentration time, and rainfall stops at this time. That means rainfall duration is equal to the time of concentration, and the subsequent flows are no longer concentrated because not all the catchment is contributing at that particular time. Therefore, when the rainfall stops, the flow gradually recedes to zero and the recession limb is asymptotic, and the effective rainfall is also shown in the figure. This is the concentrated catchment response. All right. I have shown a typical hydrograph, and this is concentrated catchment response. And in this type of catchment response, usually these two are equal, the rainfall duration and the time of concentration. All right. The next one is super concentrated catchment. This is a typical hydrograph for a super concentrated catchment. You can see it here. This type of response occurs when the rainfall duration exceeds our time of concentration. When a rainfall duration in a particular catchment exceeds the time of concentration, we get a response from that catchment which is known as the super concentrated catchment. And this type of response, as already stated, it occurs when the rainfall duration exceeds the time of concentration. In this case, the runoff concentrates at the outlet. All right, it reaches its maximum or equilibrium rate after an elapsed time which is equal to the concentration time. Since rainfall continues to occur, rainfall duration is larger than the time of concentration. Rainfall continues to occur, all right, and the runoff continues with it too. After the rainfall has stopped, the flow gradually recedes to zero. All right. So this is about the super concentrated catchment response. In this type of response, rainfall duration exceeds the concentration time. All right. So rainfall occurs at a longer duration than the concentration time of that particular catchment. And in this case, the runoff concentrates at the outlet. It reaches its maximum or equilibrium rate after an elapsed time, which is known as the concentration time. After this point, the rainfall continues to occur and the runoff continues with it too. After the rainfall has stopped, the flow gradually recedes to zero. All right. And this is a super concentrated catchment response. All right. So in this type of catchment, our rainfall duration is more than the time of concentration. Flow reaches its maximum equilibrium rate. It continues as the rainfall goes on continuing. The runoff continues. Rainfall stops. It gradually recedes to zero. All right. The next type of catchment response that we have is the sub-concentrated catchment. All right. This is a sub-concentrated catchment. In this type of response, the rainfall duration is shorter than the time of concentration. All right. We get a sub-concentrated catchment response when the rainfall duration in that particular catchment is less than the time of concentration of that catchment, and the flow at the outlet does not reach its equilibrium state. After the rainfall has stopped, the flow gradually recedes to zero. All right. The flow gradually recedes to zero. So in this type of sub-concentrated catchment response, the rainfall duration is shorter than the time of the concentration, and the flow at the outlet does not reach its equilibrium state. After the rainfall has stopped, the flow will gradually recede to zero. All right. So this was about the types of catchment response: the concentrated, the sub-concentrated, and the super-concentrated. All right. This is the concentrated one. Concentrated catchment response. All right. The super concentrated catchment response and the sub concentrated catchment response. Subconcentrated catchment response, we have rainfall duration less than the time of concentration of that catchment. In superconcentrated catchment, we have rainfall duration which exceeds the time of concentration of that particular catchment. And in the concentrated catchment response, we have them equal. The rainfall duration is equal to the time of concentration. All right. So this is discharge and this is the maximum discharge over here. All right. So this was about the types of catchment responses.